Hi everyone, I'm Minglang Yin. So welcome to the Crunch seminar. So today we have two speakers as usual. So our first speaker is Xinyang Chen. Xinyang graduated from Tsinghua University, major in electrical engineering in June 2017. So Xinyang is currently a PhD candidate at Tsinghua University, advised by Professor Mingsheng Long. His research interest focuses on transfer learning and adaptation. So today he'll be giving a talk entitled Domain Adaptation Methods for Deep Regression. So please join me and welcome in Xinyang.
Okay, can you see my screen?
Yes.
Okay, and today I will introduce my paper, Representation Subspace Distance for Domain Adaptation Regression. Because my English is not very good, so if you have questions, please tell me and we can discuss it. So let's start. First, I will introduce the background. We all know that the success of deep learning relies on large-scale label data. And in ImageNet, we always have more than 1 million label data. But in real life, we all know that the cost to collect so many label data samples is not very easy. But in some real applications, we can easily get the label samples from related domains. For example, we can collect simulated label samples or label samples from old environment. For example, in the self-driving cars, the label data from real life is not very easy to collect because in self-driving cars, we always use image segmentation. And it means that we need to label the data in the pixel level. But we can easily get the label data in the driving simulator. So how to transfer knowledge between different domains is the core solution in this problem. So we all know that in the classic machine learning, the IID assumption is very important. It means that the distribution of test data should be the same as the distribution of training data. But our goal is to transfer knowledge across different domains. It means that maybe our source domain is a synthetic domain, but the data from target domain is real data. They may have a different distribution. So the IID assumption is validated. So how to close the gap? Now I will introduce the setup of our work. It is called unsupervised domain adaptation. It means that we have a source label data x as ys and the target unlabeled data xt. Our goal is to use these two data to learn a model which can generalize well to target domain. We assume that the source data are sampled from distribution Q, distribution P, and the target data is sampled from distribution Q. So there are three assumptions in this setup, and the first one is covariance shift. It means that the PS is not equal to QX. It is a mainstream of this field, and it is also our focus. And the second one is prior shift. It means that PY is not equal to QY. It is very challenging. And the third one is conditional shift. It means that the PY given X is not equal to QY given X. It is also very challenging. So there are many pioneer works in this field. And the first one is a theoretic work from Shaban David, a theory of learning from different domains. He just want to try to relate target risk to the source risk. The conclusion is the same as this equation. And the proof is also very easy. It just uses the triangle inequalities of the loss functions. And in the first line, it is just a triangle inequalities. And the first one, it is also a triangle inequalities. So next, we will introduce what this term means. and how to bound the target error with the source error. So in the work of Shep David, he first defined a symmetric difference hypothesis space. It means that for the hypothesis space H, we can find two different hypotheses H and H prime. The result of GX, it means that if the prediction results of these two hypotheses is the same or not. So with this definition, we can define H delta H distance. It is a distance from this symmetric difference hypothesis space. It is just the disagreement between two hypotheses in hypothesis space H in distribution Q minus the disagreement of two hypotheses in hypothesis space H in distribution P. So we can find that in the this inequality, the second term can be bounded with H delta H distance. It's just two specific hypotheses, but in the definition of H delta H distance, the hypothesis is not selected. And then Shep David defined ideal joint hypothesis as H star. H star means that we find a hypothesis from hypothesis space H, and it has a smallest error in distribution P and distribution Q. So with this definition, we can explain this bound as the target error can be bounded with the source error and the discrepancy between source and target, and hypothesis subspace distance. And ideal joint hypothesis. So in this work, it has an assumption. It is ideal joint hypothesis is very small and it is constant. So it means that we can minimize the H delta H divergence to close the domain gap. And however, H delta H distance is very difficult to compute and optimize. So how to design algorithm to close the domain gap? In these years, there are many deep learning algorithms are proposed to close the domain gap by learning transferable representations. For example, domain adversarial training of neural networks, we call it DAN. It is a implementation to close to define a upper bound of H delta H distance and minimize this upper bound. We can find that in the fourth line, we just use a neural network hypothesis space to replace the H delta H subspace, H delta H hypothesis. So the hypothesis space is enlarged, and this is inequality. What is this term means? It means that we can give a neural network D. When we give a source sample, if we predict it as a 0, it means that we predict the prediction is right. And when we give a sample from distribution Q, if we use D to predict it as a 1, it means that the prediction is right. So if we predict it's wrong, it means that if we predict the samples from source domain or target domain, which is right, it means that we find the upper bound of H delta H divergence. So that's the motivation of this algorithm. It is very easy. On the one hand, it uses a domain discriminator to optimize the upper bound, and then it tries to learn transferable representations to minimize the estimated distance. Let's see the architecture. We can find that in the architecture of DAN, we have a feature extractor GF and a label predictor GY. And then he used a domain classifier GD to discriminate the samples is from source or target. So on the one hand, this is a minimax scheme. On the one hand, they try to learn domain classifier to classify the samples is from source or target. On the other hand, they try to learn feature extractor to minimize the estimated distance. It means that the feature extractor is just try to confuse the domain classifier. And if the domain classifier can classify the source sample and target sample right, it means that the estimated distance is close to the upper bound. And if we try to minimize the distance, it just means we learn feature extractor to confuse the domain classifier. There are also other classical works. Is similar. For example, this work try to use multi-kernel learning instead of neural networks to estimate the upper bound of delta H divergence. And it is the same as DNN. It try to learn representations to minimize the estimated distance. So there are very classic works in deep domain adaptation, and there are two common baselines in this field. So the basic idea in this method is very easy. First, we try to use a supervised training in source. It means that we want to minimize the first term in the bound. And the second, we want to estimating distance between source and target using max gain. For example, we use neural networks in DNN and multi-kernel learning in DNN. And in this case, we can estimate the upper bound of delta H divergence. Then we try to learn feature extractor to minimize the estimated distance. So the goal is to minimize the first term and the second term in this bound.
What is lambda? Is it just a threshold?
It is an ideal joint hypothesis. In the definition of Shaban-David, he assumed that it is a small constant. It means that we can find a hypothesis in hypothesis space H to classify the source sample and target sample correctly. It means that we can have all the labeled source sample and all the labeled target samples, and we try to use a classifier to classify it. If the samples is very easy to classify, it means that the ideal joint hypothesis lambda is very small. It is just like the discriminability of our feature representations.
Yeah, thank you.
Okay, and this works just try to minimize the delta H divergence. And also in these years, there are also many works point out that in the deep domain adaptation methods, lambda is enlarged. And some works just try to minimize the lambda to make the model performance better. But in this topic, in my presentation, I do not introduce these works. So we can find that these works are very similar. They just try to estimate distance and then try to minimize the estimated distance. And in the literature, there are also many works just try to use intuitive idea for classification instead of minimizing estimated distance. For example, this is a ICCV paper. It just try to use visualization techniques to say what properties of feature representations is good for classification. He found two observations. The first observation is that because the source samples is supervised training in the model, so the source samples always have a large feature norm. So it is just very far from the 0 point. And the target samples is always very small, always have a very small norm. So the first observation is that source feature norm is very, very large and the target feature norm is very small. And the second observation is that the second observation is the source samples and target samples should be the second observation is that if a feature have a small norm, it means that it is very easy to misclassify to other classes. We can say that if the feature is very close to the 0 point, it is very close to other classes. It is very easy to be misclassified. So in this paper, the authors say that if the feature representations have a large norm, it is more transferable and will not easy to be misclassified. So this is the main idea of this work. So I think the core insight in those deep domain adaptation methods is minimizing estimate distance or using prior for classification. So they always try to supervise learning in source data and learn transferable representation using both source data and target data. But there are still other questions. For example, we find that all these methods worked well for classification tasks, but this deep domain adaptation methods for regression are less pronounced. And also there are many prior methods for classification are used. So we want to ask if there are any differences between regression and classification in domain adaptation. For example, larger norm is a good property for representation in classification. But if it is also good for representation in regression, we want to explore this difference. First, we all know that the main difference in machine learning between classification and regression lies in the loss function. It means that in classification, we always use a cross-entropy loss with a softmax activation. And in regression, we always use a L2 or L1 loss with a sigmoid activation. If we do not normalize the label, we can reduce the sigmoid activation. So what may happen if prediction results have larger norm? We can find that because softmax activation is a normalization techniques. So if we have a larger norm for prediction results, in classification, the results will have a higher confidence, but the same prediction. But in regression, because sigmoid is not a normalization technique, so if we have a larger norm for prediction results, we will have a larger prediction values. So we want to conduct experiments to verify our idea. So we can see in the first figure, we conduct experiments in regression dataset. If we try to control the Frobenius norm of feature matrix, we find that when we change the Frobenius norm of feature matrix, the performance of the regression has been changed. We use mean absolute error as our regression performance. And in the second figure, we can find that if we change the Frobenius norm of feature matrix, the accuracy of classifier will not be changed. It means that deep classification or classifier is very robust to feature scaling. If we change the feature scale, the performance will not be changed. But in deep regression, this is not the case. And in the third figure, we use some domain adaptation methods, for example, DAN or AFN. And we found that if we use these domain adaptation methods, the Frobenius norm of feature matrix will be enlarged. So the second conclusion is that some deep domain adaptation methods significantly change the feature scale and leading to the risk of performance degradation. So I think this is very similar to the other findings in the community. It is a calibration issue. In this newspaper, the authors use ECE to measure how much confidence is higher than accuracy. We all know that in classification algorithm, we always output a value if we have a very large value, for example, very near to 1. It means that we're very sure that the sample can be classified to this class. So if we have a very confidence, but the accuracy is not the equally large to the confidence, it means that we meet calibration issue. So in the figure, you can see that if we use domain adaptation method, the ECE loss will be enlarged. It means that using domain adaptation method will cause a higher confidence, but not equally higher accuracy. So I think these observations are similar. Using domain adaptation methods will lead to larger norm for representations and higher confidence in classification. So from the above observations, we can find that the feature norm invariance is very important for domain adaptation regression problem. So question is how to maintain feature norm while learning transferable representation. Using single value decomposition, next we will call it SVD. We can get feature matrix of orthogonal bases and single values. We can say in this equation, we can decompose the feature matrix Fs to the orthogonal basis Us and single values sigma s. And the Fourier norm of feature matrix is only influenced by its single values. We can see in the second equation, the Fourier norm of feature matrix is not influenced by orthogonal basis. So our solution is to close the domain gap, only use orthogonal basis and without use single values. So there are many mathematical tools can measure the distribution between two subspaces only using orthogonal basis. And the first one is Glassman Manifold. It is also called Glassmanian. The Glassmanian Kn is a space that parameterizes all k-dimensional linear subspace of the n-dimensional vector space. It means that if we use a deep learning model, we have a feature matrix. It consists of a batch size of instance representation. So this feature matrix lies in Glassmanian Bm. B is the batch size and M is the feature dimension. So if our feature matrix all lies in the Glassmanian, it is easy to use some similarity measurement in the Glassmanian. And the principal angle is a commonly used similarity.
Excuse me. Hello. Can you
pardon?
hear me? This is Lulu. I have one question here. So here the Glassmanian the matrix depends on the batch size, but I think this kind of, let's say this kind of measure should be a property of the space. So why it should be depends on batch size? So no matter whether I train with different batch size, so intuitively this kind of should be this kind of let's say Glassmanian should be some property of the space itself instead of depends on the batch size.
Okay, I think it is the common method for deep domain adaptation. We all know that if we want to close the domain gap, we need to use more samples from source domain and target domain to estimate the distribution. But in fact, in the deep learning algorithm, we can always use a batch size of samples to minimize this distribution. For example, in the some in DNN and DNN, they all just use the batch size of samples to estimate the distribution of source domain and target domain. And it works well in the domain adaptation setup. So
okay.
I think it is true that if we just use a batch size of samples to estimate the distribution, it is not very accurate. But I think it is enough for deep learning algorithm.
Okay, thank you.
Okay, so now we can use a similarity measurement in Glassmanian to define distance. We use principal angles. It means that the first principal angles is the smallest angle between the orthogonal bases in one subspace and another subspace. And the second principal angle means that if we reduce the first orthogonal basis in source and the first orthogonal basis in target. In the left orthogonal basis, we can calculate the smallest angles between other orthogonal bases. So with this definition, we can define our representation subspace distance. It is just the sum of some values of orthogonal some values of principal angles. So it is a new defined distance. So we need to show it satisfies the three axioms for general metric. It should be non-negative, and it should be symmetric, and it should satisfy the triangle inequality. So we define the representation subspace distance. How to minimize this distance across domains? Here's the implementation in the deep learning algorithm. I think there are three stages. The first stage, we need to get orthogonal bases in representation subspace using feature matrix and SVD. We can find that we can decompose the feature matrix in source, and we can get the orthogonal basis in source. And then we can decompose the feature matrix in target, and we can get the orthogonal basis in target. And the second stage is to calculate principal angles using orthogonal basis and SVD. It is just like we can use SVD to decompose this term, and we can get our principal angles. This is the principal angles. It is just the cosine value of all principal angles. So with this calculation, we can calculate our representation subspace distance and use it as a regularizor to close the domain gap. So what we find is not very reasonable is that in the first stage, we used the SVD to get orthogonal basis. But we find that each orthogonal basis is corresponding to different singular values. What it means? It means that, for example, we have an orthogonal basis which has a singular value for more than 100. It is very large. It means that this orthogonal basis is very important in this feature matrix. But if we have an orthogonal basis which just has very small singular values, for example, it just has one single value, it means that this orthogonal basis is not very important to this feature matrix. Maybe delete it is not is okay for this feature matrix. So what I mean is that different orthogonal bases has different importance. It is not equally important, but in the calculation process of principal angles, we ignore the singular values. So it means that all orthogonal bases are equally important in the calculation process of principal angles. So I think this is not very reasonable for deep learning algorithm. So this is called mismatch issue. We can see in the figure that this is the calculation process of principal angles. Principal angles is the angle between principal vector. So what is principal vector? It is the weighted sum of the orthogonal bases US. So and we can have a corresponding weight vector P. It is just like in this equation, we can use this term to the left. It's just like PS US, and we can use this term to the right. It's just like PS US multiplied UT PT. So so it means the principal angles is calculated by the weighted sum of orthogonal bases. So we find that it is possible that the very important basis U1S, which has the largest singular value in feature matrix, and an unimportant basis UBT, which has the smallest singular value, can be matched if we only use SVD. If we only use ISD. So we find that different orthogonal bases is not equally important. Some bases is very important and have large singular values, and others may have small singular value and is not very important. So we need to consider the importance of different orthogonal bases in the calculation process of principal angles. So how to regularize the equally important bases to be matched together? So we propose basis mismatch polarization. We call it BMP. It just tries to make the weighted matrix to be similar. So if the weight matrix is similar, the equally important bases can be matched together. So we can find that all our regularizer, including ISD and BMP, only use the orthogonal basis in representation subspace, while other domain adaptation methods always use the instance representation. So I think our method have the property of feature scale invariance. So this is our loss function. And the first, we have supervised learning on the source domain. It is just an L2 loss. And the second is to use two SVD to calculate our representation subspace and principal angles. And the third part is to maintain the importance of different orthogonal bases in the calculation process of principal angles. So this is our final loss functions. And this is our architecture. We can find that we try to learn transformer representation to close.
Sorry, can you show, hold on, can you go back to the loss function a little too fast? And how do you take the weights, the beta and the gammas? The weight in the loss function?
Okay, it is just use the cross validation method in domain adaptation. In the domain adaptation literature, we always have some cross validation methods which consider the distribution shift of source and target. For example, we can use importance weighted cross validation. It means that we can use the distribution of source domain and the distribution of target domain to estimate the difference between distribution P and distribution Q. And then we can use the classic cross-validation methods to define the trade-off of our regularizer. Beta and gamma are also regularizer in this method. It means that it is not always, it is not equally important with to this loss.
And here you need to recompute the SVD every epoch, right?
Yeah, we need to calculate SVD for every iterations.
Yeah. Okay, thank you.
So in the literature, the SVD calculation is not very time-consuming because the batch size is always not very large. So the backward of SVD is not very cost. So this is our architecture. The first stage is that we use the feature matrix of source domain and the feature matrix of target domain. We can use SVD to decompose it to the orthogonal bases US and UT. Then we use the third SVD to calculate our principal angles and our weight matrix P. And then we can use principal angles to calculate our representation subspace distance and use the weight matrix P to calculate our basis mismatch penalization. So this is the architecture of our work. And now we can see our experiments. There are three benchmarks. The first benchmark is disvaries. It is a very easy 2D synthetic dataset with 6 transfer tasks. It has 3 domains. The first one is color, and the second one is noisy, and the third one is screen. In this task, we have 4 regression tasks, and we use 3 of them to test our performance. And here's the result. And we show the sum of all regression tasks of mean absolute error across the 3 regression tasks. We can find there are many baselines. For example, DN and DN we introduced before, and the AFN is the larger norm. And we can find that the DN and DN is also worked well for regression tasks. And our method outperforms this method. And the idea of AFN is to make the representation larger, the normal representation larger. So it is not worked well for regression because the Fisher norm invariance is very important for regression tasks. So the third benchmark, the second benchmark is MPI-3D. It is more challenging because it is a simulation to real 3D dataset with 6 transfer tasks. And there are 3 domains. And we can find, for example, the toy domain is a synthetic domain, and the other 2 domain, for example, real domain is a real data set. So this is a simulation to real transfer tasks. And in these tasks, there are 2 regression tasks. It is the horizontal axis and the vertical.
Yeah, can you, from the pictures, can you tell us what do we transfer to what? Just can you go back to the pictures? What is the transfer process here?
Pardon?
So synthetic is Q, and real is P. Is that what we're doing? I'm trying to identify the domains Q and P.
Okay.
Yeah.
Synthetic to real means that we have labeled data from a synthetic picture, and we have unlabeled data from real picture. And we want to train a model which can generate real in the real domain.
Right.
So it's a simulation to real.
Right. So the Q is the synthetic, the P is the real.
In fact, we have 6 transfer tasks. We can use the synthetic domain as source domain, and we can use the real domain as target domain. And we can also change it because, for example, we can use the real domain as our source domain and the synthetic domain as our target domain. It is also okay. For example, in this task, toy is the simulation dataset, and real is a real dataset. And in our experiments, from real to toy is from real to simulation, and from toy to real it means that we from simulation to real.
Okay.
So in our experiments, we just use these 3 domains and conduct 6 transfer tasks. It means that we can transfer from toy to realistic and transfer from realistic to real. So we can get 6 transfer tasks. So our result is the average of these 6 transfer tasks. And we can also find that DN and DN are also works well for this data set. And our method outperforms this method. And the third one is a real world data set. We just use 2 domains. The one domain is male and the second domain is female. And in this experiment, we also have 3 regression tasks. So this is the result of our method. Because this data set just has 2 domains, so we can establish 2 transfer tasks, male to female and female to male. We can see that our method.
I have one question. So what's the output of these experiments? The input is image. What's the output? Is it a scalar or?
Output is this vector. It is just the angle in the 3D world. For example,
3 numbers. Okay.
For example, the people just do like this, and if they just do this type of actions, there are 3 angles in the 3D world. So the 3D world is the 3 angles is our regression tasks. So the output is the 3 angles.
Okay.
So this 3 factor is just the 3 angles in the 3D world. Yeah.
Okay, thank you. Is it possible to do a simple, let's say, I try to regret y is equal to sine x function, 1D function. Then the source domain is x is sampled uniform between let's 0 to 1. The target domain, let's say x is in Gaussian distribution or some other distribution between 0 to 1. Is it possible to do this kind of simple tasks instead of images?
I think it is okay, but it is more difficult because it is more random values. In our experiments, they are always very uniform distributed from some values. For example, in this data set, we can find that there are 40 values from 0 to 1. They are uniform distributed because it is just try to collect picture with the human itself. But in the real world, we all know that some regression tasks may have very random values. So it is more difficult.
Okay, thank you.
So in these experiments, we found that our method leads to marginal improvements. We think it may be because that the two domains are not very far away between each other, because the male and the female is not very different in these three tasks. So the discrepancy between source and small is very small. So the discriminant between source and target is very small. So the transfer learning is not worked well in this data set, I think. So there are other perspectives. So we all know that there are some very important normalization techniques that works well in the deep learning architecture. For example, batch normalization. It is very important for deep learning. If we use a batch normalization model before regressor, it can maintain feature scale. So in this PAMI paper, we can find that it is shown that batch normalization before regression cannot work well for regression tasks in ResNet. So we conduct experiments to confirm this point when we have different domains. And we can find that if we add batch normalization before regressor using ResNet or DAN, the performance will be worse. So it means that batch normalization is not very good for regression tasks, especially when we use it before regressor. So, and there are other perspectives. For example, there are also many existing metrics in Glassman. Why we try to define a new distance instead of existing metrics. For example, geodesic distance is commonly used metrics in Glassman. So I think in the representation learning process, gradient is the key to the problem. And we can find that the ISD use a sine function and L1 norm, and the geodesic distance use L2 norm. So ISD can give a larger gradient to the minimum angle, and the GD gives a larger gradient to the maximum angle. What it means? It means that when the two domains are very different, there are many representations should be different and should not be close the distribution between them, because some feature representations are not very important for our regression tasks. So try to close the gap between them is not very important. So our ISD try to close the gap between the minimum angle. It is more reasonable. So we conduct experiments to confirm our point. We can find that using geodesic distance will have a worse result, and it can have a larger cosine value in small pixel angles. So we think that IC is more reasonable for representation learning, And the GD is a well-defined distance, but it is not very reasonable for representation learning because its gradient is larger for maximum principal angles. So I think this is a very easy exploration because we just use the easy data set and works well in limited scenarios. Because we are the first work in deep domain adaptation regression, and other works are always works well in domain adaptation classification. We think there are also many works we need to explore in regression problem. So, for example, there are still other issues. The first one is random regression values. We just talk about this. It means that in some of our data sets, regression values are not very random. They are uniform distributed in from 0 to 1. For example, the position x is it is uniform distribution from 0 to 1. It is not a real random. So, but in some real applications, the regression values may be very random and it is irregular. So this is a very difficult problem. So, and there are also other difficult problems. It is just like the long-tail distribution in classification. It means that we cannot always get samples which are equally, which had equally num in different values. For example, in this figure, we can find that there are more samples from 20 to 40, but in other regression values we can have less samples. So it means that the distribution of regression values is not uniform distributed. So in these scenarios, the algorithm will the performance of our model will be degradation. So I think it is a more challenging problem in regression problem. So and there are also a transfer learning library in our research group. In this library, we just have many algorithms. For example, domain adaptation, model adaptation, and other setup. So this is the that's all of my talk. Thank you. If you have any questions, we can just discuss.
Thank you, Xinyang. This is an excellent talk.
Xinyang, I have a question.
Oh, okay.
So we are interested in solving PDEs, which is regression, and so do you think it's possible to solve a PDE in one domain, let's say a square domain, and then transfer that to a rectangular domain, which is not very far from, in other words, the domain here is the geometry where you define the problem. It's not the task that you're doing, it's that you had, but like actually the domain of defining the problem, the support, let's say, of, you can think of the support of the function that you regress. Is that a domain adaptation problem? I want to transfer my solution that I find in one domain to another domain, geometric domain.
Can you explain it again?
Maybe Lulu can explain to you. Lulu.
Yes. So basically, so the input is a function defined on different domains. So here your input is always an image, a rectangular image by uniform grids. But if you consider input, it can be different. So we have some inputs, let's say, defined on a rectangular domain. So the input is the rectangle. Another, this is our source domain. Then our target domain could be some triangle inputs or something else. Do you think this is possible?
I think the core problem in this setup is the value of these two domains can be measured. It means that in the two measure space, matrix space, for example, in source domain, the 0 to 1 is it means that just 0 to 1, but in the another domain, for example, maybe 0 to 1 is just like the 0 to 2 in the source domain. So it means that it means that if the number in the two domains can be measured together, I think it can be transferred. But if the matrix space is different, it is more difficult and it's challenging. So I don't know whether I understand your problem. So I just want to say that the matrix space is very important. If it is equally in two domains, it can be transferred. But if the matrix space is different, it will be more difficult.
Yes. Yeah, and also for the output. So for the output, usually if we consider PDEs, if we have different types of inputs, different domains of the inputs, then for the outputs, they are definitely not uniform as in your task. Also, it makes more challenging.
Yeah, I think it is random. It's okay then then it is not uniform distributed and it is random.
But can I remind you guys that what Xinyang is doing is similar to what Katyana from Johns Hopkins was doing on a Grammanian manifold, where she was trying to do a reduced order model. And she was basically getting the same distance and the angles, if you recall. And that's, of course, was PDEs and so on. But of course, there was not changing the domain. It was just changing the representation to make it a reduced representation using the Grammanian. And there are other manifolds one can use. So, but the procedure is the same, basically. And the comparison for similarity. You may recall the talk that she was doing about UQ. It was a couple of months ago.
George, hi.
Yeah,
Hi, this is Panos Tinis from PNNL. I don't know, I think that because our speaker is mentioning the case of a distance, a geometric distance, maybe if the domains are somehow topologically equivalent, so in the sense that even though they look different, they're really not different, maybe there is some space where they're close. Okay, so maybe there is a representation of these domains where they're close, and if they're close, then this approach maybe can be applied.
Yeah, that's why I told him
right.
Square.
Exactly. So if you take a square and the rectangle, which are close to one another, there has to be some kind of feature space where these things are very close.
Yeah.
Right? Because in the sense of topology, they're the same. You can deform one into the other. So basically, I think that if you can deform one into the other, it should be possible to apply this technique.
The reviewers are
Yeah. Yeah, I hope so.
Any other questions? Well, if not, let's thank our speaker again. Thank you, Xinyang.
You are welcome.
So our next speaker is Yao Li. Yao Li is currently an associate professor at the Department of Mathematics and Statistics at the University of Massachusetts Amherst. He received his PhD from Georgia Tech in 2012. His research area is applied probability and applied dynamical systems, including topics related to statistical physics, machine learning, and the neurosciences. Recently, he's particularly interested in understanding the interplay between dynamical systems and data-driven approaches. So today, Yao Li is going to give us a talk entitled Data-Driven Computations or Invariant Probability Measures. Yao Li, you may share your screen. You're mute. You're muted.
Oh, sorry, I'm muted. So let me share the screen. Can you guys see the screen?
Yes.
Good. Yeah, so thank you very much for the invitation and the introduction. So as Ming-Lang said, that my research field is dynamical systems and applied probability. So I'm relatively new to the field of machine learning, but yeah, recently I'm spending lots of time on that. I'm very interested in the interplay between data and dynamics. So it's actually two directions. So one is that what could a modern machine learning technique help us to solve classical problems in either probability or dynamical systems, which is essentially what I'm talking about today. And the other thing is that so how could the dynamical systems helps us to understand the mechanism of deep learning? So there are also something ongoing about that. So today, let's talk about some of the recent results in my group about the data-driven computation for invariant probability measures. So yeah, so basically we are going to use simulation data to estimate either the invariant probability measure or its ergodicity, means how fast does it converge to the steady state. So why do we use the data-driven? It's because the traditional methods in general it only works in 2D, and you will need lots of preparation and computing resources to do 3D and higher than 3D. So it does not really work. So basically, I'm going to talk about three things. One is that if we have something stochastic and high dimension, then how can we solve the invariant probability measure? And the second question is more like a mathematical question, but it's a very important mathematical question. So the ergodicity of the invariant probability measure. In other words, how fast does the process convert to its steady state? So it has lots of applications, and I just mentioned one of them. It's called the sensitivity analysis. So it's like, okay, so now if I perturb my system a little bit, then how much would the invariant probability measure change? So you're going to see that actually these two things are equivalent. And if you have a good estimate of ergodicity, then good, you have a very good control of the sensitivity. So that's one of the reasons why this ergodicity is so important. So just let me start from the very basic thing that if you have some ordinary differential equation, I mean, today let's just talk about the finite dimensional problems. So if we have some ordinary differential equation and we add some noise into it, just some white noise. Let's not do any fancy thing like color noise. So just some simple white noise perturbation. Okay, and then we all know that, well, then it gives us some continuous time Markov process. And this Markov process, it has a timely dependent transition kernel, which means, okay, so Pt of xa means I start from x, and after time t, what is my probability of getting to a set A? Okay, then we from this transition kernel, well, it generates a semigroup, and this semigroup has an infinitesimal generator. So which means if U is any test function in the domain of this generator, okay, so I let this transition kernel act on U and minus U, and okay, so what's the derivative? We all know that, well, this derivative is a second order differential operator. So this is called the Fokker-Planck operator. Okay, and what is A? A is just sigma sigma transpose. Okay. So here I keep a parameter epsilon because I want to address this thing later on. So that if epsilon is very small, then you are going to see some very interesting interplay between noise and dynamics. So anyway, so let's talk about how can we compute the invariant probability measure, because I mean, of course, there are lots of study about uniqueness and existence and so on. Well, that's a different topic. Okay, that's a very different topic. But the thing is that it's relatively easy to show the existence. But after you have the existence, what does the invariant measure look like? And where do you have concentration? Where do you have high density, low density? That's not something the theoretical proof can tell you in maybe 90% of cases. So that's why we need some computation. So what is invariant probability measure? It means, so well, we have, as I said, there is a transition kernel for this stochastic differential equation. And then if you take the left operator of this transition kernel, you let it act on a probability measure mu, and it does not change, then it's invariant. So in the so heuristically, it means if you start from something and then you run this system, and after a while, if you find that this probability measure does not change, okay, it is invariant. And obviously, the invariant probability measure, it should satisfy the steady state Fokker-Planck equation. In other words, you take this infinitesimal generator L, and then you take then you find its adjoint called L star. Okay, then the steady state Fokker-Planck equation, it is L star U equal to 0. And if under the constraint that U is a probability density function, good. So U is invariant. U is invariant. Okay. So that's some mathematics, some mathematical background. I mean, here we just assume that we have existence and uniqueness, because actually the condition for that kind of thing is relatively mild. So as long as you know that there are some dissipation very far away, then you should be good. But as I said, again, you know the existence does not mean you know what the invariant measure look like. So just to give you a very simple example, so if you have some Rossler attractor, so you have some chaos, okay, and you add some noise into it, and so how would the steady state look like? And the answer is that it looks like this. So I mean, this is a projection onto the XY plane, because it's hard to visualize a 3D density function, but you can see that it looks like this. And well, usually, I mean, the theoretical proof, it's very hard for you to prove that I have a high density here and I have a low density here, and the shape of attractor look like this. And also, this is very interesting because we think the noise gets smaller and smaller. Then you should, I mean, heuristically, you should see more and more dynamics. And in this scenario, so how would the dynamics interplay with noise, and what does this invariant measure look like? And for example, we all know that this kind of strange attractor, they have the non-integer dimensions. Then how does this non-integer dimension reflect on the invariant probability measure when the noise gets smaller and smaller? So all of these questions are, I would say, largely open. Okay. So anyway, let's go back to the computation part. So how can we compute the invariant density function? Well, I know this is a talk to the machine learning community, but let's first talk about the classical approach. Why? Because actually you can say that this classical approach is motivates the neural network solution. So how do we solve it? Assume that we do not know neural network. We assume that we were like 40 years ago. We only know some basic numerical PD approach. So of course you should try to discretize this operator. Okay. So after the discretization, is it solved? Well, yes and no. Because Fock-Planck equation in general it is defined on the infinite domain. Then a natural question is that how are you going to set up the boundary condition? So the common practice is that, oh, let's make the domain big enough. And we have the large deviations, which means if you are really, really far away, then your density is really, really low. So let's just assume that it is 0. But then 0 boundary give you 0 solution, which is not good. Actually, we are looking for the first eigenvalue. Okay. So then which means you have to add a constraint that the integration is 1. And then it becomes a least square problem. So you solve a least square solution. So you can see that in general, the computational cost is unnecessarily high because you have to make a domain really big to assume that the boundary has 0 density. But that's the foundation. That's the foundation of every new approach. And the other approach is that, well, let's just forget about accuracy. We just do Monte Carlo. We just divide the domain into lots of small bins. And then we run a very long trajectory of this SDE. And let's count the samples inside of each bin. Let's estimate the density. So it works for arbitrary domain. You don't have to worry about the boundary condition at all. But I mean, if you have ever run it, you will know that it's not accurate at all. There are high relative error. I mean, you use some kernel density estimator, it can improve a little bit, but still you are always expecting, you should always expecting some very visible error if you run Monte Carlo and to get compute some something like invariant density. The solution looks very furry, lots of local fluctuations, even if your sample number is large enough.
Can I ask a quick question here?
Okay.
So this is Yanjong from Brown. So your transition probability may not invariant in the first place. So are there any studies that how fast it will converges to the invariant?
That's the second topic. This is called the algorithmicity. So
okay, I see.
Yeah. So I mean, of course it matters. I mean, if it converges turtle slow, then you have to wait a long time. And actually, later I'm going to show you that in that kind of scenario, the accuracy of Monte Carlo is even more questionable because I mean, slow convergence means you are dramatically amplifying the finite time error to reflecting to the invariant. I'm going to show you later on.
I see. Thank you.
So just to show you some quick example that it's nothing but a gradient flow. So the gradient, the bottom of this potential is a unit circle, and then I add some rotation just to distinguish it from a trivial gradient flow. And then you know what's your invariant. And so you have this very good vector field. Okay, we call this ring example. And what does the Monte Carlo results look like? So after you run like 100 million samples, it looks like this. So it's not, as I said, it's not usually the result from Monte Carlo. It's not very accurate. Okay, so how can we combine the advantage of these two approaches? So this is called the data-driven PDE solver. Well, let me first talk about the lower dimensional version because the neural network version is actually really motivated from this guy. So the idea is that, well, the difficulty of PDE solver is that you don't know the boundary condition, and the difficulty of Monte Carlo is that it's not accurate. So let's do the following. So let's throw away the boundary condition in PDE. Okay, so which means I mean it does not have to be a finite difference. It can be also other schemes, but I mean just use the finite difference because that's easiest to explain. So let's just take the spatial discretization of this operator. Okay, and then you just throw away all of the boundary conditions, and also you only discretize it in the interior grid points. So for example, if I have 5 points, then I only find the discretization of the center 3. Okay, then well, we have a linear constraint. We have a linear constraint. I call it AU equals 0. So this A is the discretized Fokker-Planck operator, but it's not a full matrix because we do not consider the boundary condition. Okay, then let's set up an optimization problem because I want to use the Monte Carlo data. So let's run a Monte Carlo simulation. It doesn't have to be very accurate. It's okay to keep a very large amount of noise. It's actually okay, as long as your noise is unbiased. Okay, so just run some Monte Carlo and you have some very noisy solution. Okay, then I call this reference solution V. So let's solve a variational problem. So subject to AU equal to 0, which means you let this discretized Fokker-Planck operator act on your solution, it should get 0. And this gives you a hyperplane. Okay, this gives you low dimensional hyperplane. And you are going to minimize the difference of U and V under the constraint that you are on this hyperplane. So this is called the least norm solution, and it can be explicitly solved. So this is just V plus A transpose inverse times D. D is minus AV. Okay, you don't have to remember the formula, but it actually actually does is that I just project V onto this hyperplane, onto the kernel space of A. Okay, so as I said, this is the mechanism that so you have the exact solution. Okay, exact solution means AU just equal to 0, and V minus U. So it's from the Monte Carlo, so which means there are some random error, and this random error is a high dimensional random vector. And well, this optimization problem just project your random vector to the kernel space, and you have this projection from the dimension 1 million to like 1000. Then suddenly you are going to lose lots of its norm. So this projection greatly reduces the error. Okay, so you know it's so this method solves lots of disadvantage because we dropped the dependency on the boundary condition, so we can get a high resolution profile in wherever we are interested in. But well, you still have to solve a large linear system. So how to improve? Oh, by the way, some error analysis. So that's done by my collaborator and my postdoc and me. Well, it's as I said, the mechanism is clear that it's like a projection from high dimension to low dimension. So which means you can easily show that I have this convergence. I have this convergence result that when the grid density go to infinity, then the error just go to 0 because you have this projection. But I mean, the empirical result is actually much better. So there are a couple of reasons, but it's hard to give proof. But just the empirical performance is much better than this n-1/2. Part of the reason is that all of the error after the projection it concentrates at the boundary, at the boundary of the domain. And why? This is because well, the principal angle of between the kernel A and the theta D means the subspace spanned by the boundary. Usually they have you have pretty small principal angles. But again, this is not very easy to prove unless you just study the fit kernel. Okay, So there are some improvement about that. Well, but I think this is talk. Most of the audience are in the machine learning community, so let me go through it quickly. So one quick improvement is that, well, your solver does not rely on boundary anyway. So let's just divide a large domain into lots of small blocks. Let's do this divide and conquer. Then you are dramatically reducing the cost. So how big a block could be? One block could be so the size of one side of this block could be anywhere between 20 and 30. That's the optimal side we found. Okay, and then most of your error are concentrating on boundaries, and let's deal with the interface error later on. So it works pretty well for 3D and 4D problems, but in higher dimension, it's basically not possible to discretize the space, and it's a different story. So how do we deal with the interface error? So there are some algorithms for that actually. So I will not dig into the detail because actually there are lots of it. But the basic approach, the basic idea is that because the boundary grids accumulates most of the error terms. So let's shift the block. So when we solve it for one round, we have lots of errors concentrating on the boundary. Then we redesign the block such that the new center covers the old boundary. Okay, then we do it again. We let the old solution as the data, and we do it again. So I mean, then you are projecting your error onto the boundary again. So do it back and forth for 2 or 3 times. Then you can dramatically eliminate the interface error between blocks. So that's what I said. So if you do not do any treatment, it looks like this. You can clearly see that there are some visible error here, especially on the interface. But after this treatment, it's gone. It's very smooth. It's not just a trivial. It's not just a trivial smooth kernel. It's like you reassign the blocks and then you let this solver run for one more time. Okay, and that's the example. That's the Rosler example. So you can see that it's a very big attractor. It's a very big attractor, and when we solve it on a domain with size 2048. So 2048 by 2048 by, I think the vertical one is like 1024. So it's a huge grid. Okay, then we solve it, but we use this divide and conquer technique, and it takes us about 1 hour on a laptop. It's very efficient, and you can see the solution on all of those slides. So you can see that you cannot see any trace of the very noisy control. Everything got smooth rise. And that's the projection I showed to you, that you can really make your resolution be really high with really low cost. Okay, so that's the first part. You can see that it's just some traditional PDE, but this approach motivates the new high-dimensional version. That's based on the artificial neural network. So we know that the discretization does not work in high dimension. So in high dimension, let's just find an artificial neural network to approximate. So if you want to do this, then you have to set up a loss function, and which means you should set up an optimization problem. So how do you do it? Well, the answer is that we twist the constrained optimization problem a little bit, such that it becomes the minimum of solution minus data plus the discrete operator act on the solution square. Okay. So that's the new optimization problem, and actually we can prove that the linear version of the linear algebra version of this new optimization problem, it has a similar convergence result. Okay. Then let's do a neural network version. We approximated this U by an artificial neural network, and we change this A from the discretized operator to the real differential operator. So before we So I mean, when we after we done all of this thing, we realized that it's when we read the paper, we realized that this is something that I think many of you are very familiar. This is actually ping. It's actually ping. So if you replace this discretized operator by the true differential operator, then you get ping. Okay, so you have a neural network, and you want to use neural network to do approximation, and then there would be a parameter theta. So you want to adjust this theta, and you want to basically minimize your loss. So this sounds trivial, but I mentioned this theta because the way we optimize this problem is a little bit different. Okay, so then this seems to be like a practice of ping. Okay, so you have the Fokker-Planck solution. You use a neural network to approximate it, and then there would be two loss functions. So one loss is u hat minus theta, and the other one is L star, the adjoint operator act on u hat. Okay, then we have, of course, we have different training sets for L1 and L2 because L1 it relies on the Monte Carlo result, and in high dimension you cannot get Monte Carlo approximation of density everywhere. You can only do it for like a few hundred or maybe a few thousands of points, and the cost is really pretty high, no matter what kind of kernel density estimator you use. And also it is really, really noisy. Okay, so then it's actually a multi-scale, multi-objective optimization because you have L1 and L2. And because L2 is much, much bigger than L1 in the beginning. You know, in the beginning, your neural network, when you take the second order derivative, it can be very, very off from the real one. But when the training proceeds, it gets more and more accurate. But still, you have some very noisy data, so which means you cannot reduce L1 to 0. You can reduce L2 to somewhere very close to 0. So which means in the end, L1 is much larger. So which means it's almost not possible for you to set up a weight for L1 and L2 manually. I mean, unless you manually adjust the weight during the training. Instead, what we do is called the alternative adder. So I think this is, I think most of the audience are in the machine learning community, so you should know much more than me. So we know that the Adam optimizer, this is almost scaling free. So you have this first approximate, you have this approximating first moment, and the root of approximating second moment, and you have this epsilon. So without epsilon, it's scaling free. Without epsilon, the training process of L is the same as the training process of a constant times L. But I mean, you have this epsilon to avoid this to avoid, I mean, dividing some very small number. So as a result, it's kind of almost scaling free. Okay. So which means we make use of this property, and then let's train these two loss functions alternatively. So we find one random set of L1, and then we evolve L1 a little bit, and then we find another random training set of L2, and then we evolve L2 a little bit. So it's like you are just randomly alternating the gradient of these two loss functions by using this adder. So this is called the alternative adder. So I mean, I think this is not really new because it's a similar kind of averaging principle. You can find it in ADI, in springs, and in splitting schemes. Well, we do not really have a theoretical foundation for now. We are still working on that. We are still trying to understand what is it converging to. But yeah, it works very, very well. It works very well empirically. So let me show you some examples. So if we do the same ring example, but in 4D. Okay, in 4D, so we have this 4D sphere, and then we add some rotation, and we can again find the invariant density. So we just solve it. Oh, so you can see that here we only use I think it's 4,000 data points. So we only have 4,000 data points with density, and all the other training points without density. You just train it for the Fokker-Planck operator. And also because it's in 4D, you know, your data cannot be really accurate. You have a very high level of noise, and the result is still quite satisfactory. So you can see that you can really recover it at every single slice, because you cannot visualize a 4D density, so you can only visualize it at a slice, at a 2D slice, and it looks quite satisfactory. And then we test the limitation of this algorithm. So how high the dimension can go to? Okay. Then here we do a stochastic, a discrete stochastic heat equation. So just the discrete operator plus some independent noise. Okay. So we find that here it's that the invariant density can be explicitly solved. So we feed the neural network with the true invariant density because we just want to test the representation limit of the neural network we use. So the neural network we use, we have 128 hidden neurons in each hidden layer, and we have 4 hidden layers. Okay, so we find that it works pretty well when n equals to 10. But the neural network is probably, I think, not wide enough if n is equal to 20. So basically, just some tests about what's the limitation of our neural network. I mean, I'm not saying that this cannot be improved because we are not really working on polishing the training, polishing the neural network architecture, things like that. We just use a simple feed-forward neural network. So that's the result. So that's the true density from the exact solution, and you can see that in 10D it looks okay. And if you make the first hidden layer a little bit wider, you can see the result gets better. But in 20D, okay, so you can see that there are some artificial diffusion that the concentration is less than it should be. So I think there are 2 possibilities. One possibility is that one possibility is that we didn't train it. We didn't use a good enough neural network architecture. And the other possibility then, so this is because the neural network representation, it has some limitation. Why? Because in higher dimension, this in higher dimension, effectively this density is more concentrated, and more concentrated means you have higher derivatives. In other words, you have higher Baryon norm, and there are some theoretical results saying that this the representation error of the neural network, it is related to the Baryon norm of the target function. So that's another. That's also a possibility. And actually, we did observe that this kind of problem, that if you have some density, and this density itself, it has a very high second-order derivative. And that's the situation that you need a really wide neural network to represent it well. And that's because I think that's related to the neural network approximation theory that so basically the approximation error kind of depends on the Baryon norm of the target function. So anyway, so that's the neural network version. Okay, so actually there are, I mean, as I said, I'm pretty new to this machine learning research field, but we do find that there are some interesting things that we should work on. So one thing is that, so what does this alternating atom really convert to? I mean, the problem of atom is that it's not linear, so you cannot simply add things up. So we need some assumption, and we are still working on this. So we want to find where it actually converges to for the continuous version and for the stochastic gradient version. And how does it compare with other methods? So it's basically an averaging principle, I would like to see. And the other thing is that empirically we find that the neural network in our case, it can tolerate a really high level of noise. So the magnitude of noise can be as high as 50% of the magnitude of solution. As long as it is spatially uncorrelated, most likely you can still recover it. So what's the mechanism of denoising? And actually, I think this kind of applies to ping. So what's the mechanism of denoising? So we are now studying this neural network on the Fourier space. So the idea is that so assume that you have some solution and you have some noise, and then the feature of noise is that you have lots of high frequency terms. Okay, and then you have this PD solver, so you kind of know that the solution is in a lower dimensional space. So it's like similar to the linear algebra version that you are projecting something to a lower dimensional space. So I think that can partially explain the mechanism of denoising. So basically, you are projecting some very noisy function in the Fourier space to a much lower dimensional space. Okay, okay. So that's the first topic. The how do we solve the invariant density function? And then let me talk about the geometric ergodicity. So in other words, how fast do you have the convergence? This is very important, as Yunjun just mentioned, that well, if you have very slow convergence, then your monocurve result is not trustable anymore. So how do you estimate this speed of convergence? So again, we assume that it's Markov process, and we have transition kernel, we have invariant density, and we say that the this xt is geometrically ergodic with rate r if we have this exponential rate of convergence. Here we do not see anything about the eigenvalue spectrum, because usually the spectrum only makes sense if xt is reversible. If it's reversible, you can talk about L2 pi. But if it's not reversible, and if you work on the L infinity space, then actually it's there are some problem about that actually. So there are some problem about sometimes you may have the convergence. Sorry, sometimes that you may have special gap in L infinity, but the ergodicity may be different. So I forgot the result, but I remember that in L infinity it's a little bit different from L2. So anyway, let's just talk about the speed of convergence. Okay, so this is not easy, because you can see a very serious interplay between the deterministic dynamics and the noise. And in general, if it's reversible, there are some rigorous results to tell you how fast do you have the convergence. But for the non-degenerate case, a rigorous estimate is usually not easy, and most rigorous results rely on some Lyapunov function. And whenever you use a Lyapunov function, sorry, you cannot get a sharp result. It's not sharp. So instead, we use something called the coupling lemma. So the idea is that, well, I find something in the product space. We call it x1, x2. Such that the two marginal distributions are still your original process, but in the product space, it can do something else. It does not have to be independent anymore. And then I measure the first time when this x, or there is a typo, it should be x2. This should be x2. So we measure the first time when x1 and x2 meet with each other. So this is called the coupling time. And we know that, well, the TV norm is bounded by the tail of this coupling time. That's one forward direction. And the backward direction is that it's even better than there exists an optimal coupling such that this equality holds. I mean, you cannot construct this optimal coupling if you do not know the future, but it exists. We know the existence. So let's do the following. So, well, we just run it numerically, and we just run this coupling, and we wait until the couple. Okay, so this the coupling inequality tell you that, oh, there is a lower bound. And how about the upper bound? Upper bound is like you find some way to divide your domain into two parts, and then you find the minimum time for trajectory to cross the boundary, and then you take a record of this time. Okay, and then this crossing time, the tail of exponential tail of this crossing time, this gives you an upper bound of the geometric ergodicity rate. Why? Because if you do not cross the boundary, you cannot couple. No matter what kind of couple you use, you have to cross the boundary. So for example, if you have double well potential, then immediately you can see, oh, there should be an upper bound, and this upper bound should be your exit time from one well to the other. And then a interesting topic. So how do you couple things numerically? Well, it's a little bit delicate here because you know, numerical thing has error, and you know, if you run a theoretical coupling numerically, you have some errors. So they may just miss each other. So I mean, what do we do? So the solution is that so when this x1 and x2 are far away, we can either run them independently or synchronously, which means we use the same noise, or we use the reflection if it's driven by Brownian motion. Means we have mirroring. Means if the noise term of x1 move to left, then the noise term of x2 should move to right. So we do all of the first three things depending on the system until they are close enough. And when they are close enough, we run the maximum coupling. What does this mean? This means, let's simply compare their density function at the next step, and then we keep the common part. So, for example, we have the blue curve and the red curve, two density functions, and see this edge part, they are in common. They're in common, and then let me just couple them. Okay, so which means you have some maximum probability to couple for your next step. So you can play with this when they are close to each other enough, and this kind of avoids the problem of numerical error, and then you can show the consistency. Means if your numerical trajectory get more and more accurate, then you get then your coupling probability becomes more and more accurate. So then anyway, then you can couple, and when you have the coupling time, you can get the speed of convergence. So let me show you two examples. One is SIR model. So I use this model because it has some degenerate noise. So actually I borrow it from other people's paper because they spend lots of time to prove that you have the speed of convergence, which is faster than power law. But they don't know the actual speed of convergence. Okay, and well, it's degenerated there. So how do we couple? So the answer is that let's just use synchronous coupling. So which means these two noise terms in the coupled process are equal. You just let the deterministic dynamics drive them together. Okay, then if they are close enough, you use this maximum coupling. Okay. So it kind of shows that if your random dynamical system has some negative Lyapunov exponent, then you have a very good speed of convergence in average sense. So that's what we see. And you just run this synchronous coupling until they are close enough, and then you run the maximum coupling. And then we have this tail distribution of this coupling probability. You can see that, oh, it's a very beautiful exponential tail. And if you measure this exponential tail, you can see the slope is quite large. So this one should represent your negative Lyapunov exponent. And you can see that, oh, you actually have a very fast speed of exponential coupling. Although rigorously it's difficult to prove, but actually we see very fast speed of convergence. Okay. And the other example is a coupled neuron oscillator. It's a biological neuron. It's not an artificial neuron. So we have 50 of them, and let's have some nearest neighbor coupling and some mean field coupling, and then we give them independent noise for each neuron. There should be I, there should be one I and two I. So the noise for each neuron are independent. So we have 50 coupled neurons, which means we have 100 equations. Okay, and this way, that's the average membrane potential. So you know that in dimension 100, it's very difficult for you to solve for Planck equation, for you to calculate the eigenvalue and so on. But the coupling approach is almost dimension free. You know, you just simulate it until they couple. And here, because the noise is non-degenerate, we use the reflection coupling. Means if the X process go to left, then the right process has to go right. And then we run the reflection coupling until they are close enough. And when they are close enough, we compare its density function. So we found that yeah, it's you actually enjoy a really fast speed of coupling, which means the speed of convergence to the steady state is fast. And then we compare this numerical coupling speed for different parameters. There are two parameters. One is du, the strength of nearest neighbor coupling, and one is w, the strength of mean field coupling. Then we find that what we observed is heuristically right, because I mean, you increase the nearest neighbor coupling, means you make the solution to be, means you make neurons to be more synchronized. And the more synchronized you have, the less, the slower you are when you are converging to the steady state. Why? Because I mean, you have stronger synchronization, just means it's harder for your two trajectories to couple, and also it's harder for you to spread out to the steady state. And I mean, at least the trend is correct. So I'm not claiming that the rate we get is sharp, but yeah, the trend is correct. That when you have the stronger nearest neighbor coupling you have, the more synchronized the neurons are, and the slower the speed of convergence you have. So I mean, just this example, just that we want to use it to show that we can use this coupling in very high dimension. So one more comment I want to make is that this coupling speed, it can actually give you some information about the dynamics itself. So it may sound trivial in low dimension, but in high dimension, it's really important. So think about this simple problem that we all do artificial neural networks, and we all deal with this high dimensional loss functions. So what does this high dimensional loss function really look like? It's very hard to visualize it because we live in 3D. We cannot imagine what our 1 million look like. But we can use this coupling idea to, you know, classify this high dimensional potential landscape. Why? Because actually, when you change the magnitude of noise, remember this little parameter epsilon I showed you in the very beginning, you change this epsilon. And for one epsilon, you get one coupling time distribution. For another epsilon, you get another one. So when you collect a few coupling time distribution for different epsilon, then it's like it's like this the very old paper that can you hear the shape of drum? It's like you knock this landscape with different strength, and you get a different sound from this coupling time.
Can I quickly ask one question, clarification? So coupling goes to pairwise, right?
Yes, pairwise, yes.
Then what you have shown is shows like some
pairwise,
covariance
but you
type.
should make the two marginal distribution to be same as the process you are working on, just with different initial value.
Ah, I see.
That's why it's called coupling. So the initial values are different, but the process are the same. If you only look at the marginal distributions, but at the product space, it does not have to be dependent.
Oh, I see.
Yeah. That's called coupling, and it's a very powerful tool.
Oh, very nice. Yeah, thanks.
Okay, so then we find that so this coupling time distribution at a different magnitude of noise, you can really make it to use it to classify the high dimensional potential landscape. For example, you can check, do you have any bad local minimum? And if you have, then how deep it is. Okay, so that's some kind of our ongoing work. So I call it, can you hear the shape of a landscape? So I'm not presenting it, I'm just saying that, so actually we use lots of data science, machine learning tools to study dynamics, but the study of dynamical systems and the probability can reversely help us to study the theoretical foundation of machine learning. Okay, so the last topic, so the topic that you asked me in the beginning is actually called the sensitivity analysis. And so if you perturb the system a little bit, then how would the invariant probability measure change? And actually, that's one. I think that's part of the reason why people who study uncertainty quantification are interested in this special gap or speed of convergence or and so on. Okay, what's the question? Okay. Yeah. So so it turns out that all of this kind of sensitivity thing depends on the speed of convergence or the special gap if you work on L to pi. Okay. So let me just show you one simplest case, the simplest sensitivity analysis we can carry out. But I mean, it does not have to be like this. You can add other parameters. So we only study one type of sensitivity, the sensitivity against the discretization. So let X to be the real SDE, and let X hat to be the numerical one. You have the finite, you have this finite time steps. Okay. Then because of the discretization, there is some error. So the question is, how different is pi hat from pi? I mean, you can generalize this problem to lots of different settings, but yeah, the underlying mechanism is almost identical. That you should use the coupling to get a quantitative estimate of the speed of convergence. So basically, we rely on something called triangle inequality. So you want to measure the distance between pi and pi hat. Okay, so I let p and p hat work on pi, and then I let p hat work on both pi and pi hat. Then you separate this error into two parts. The first part is just a finite time truncation error. Okay, so that's something that we all know how to do it from the graduate numerical analysis course. And the other part, I let the same operator act on two different measures. Then I should say some concentration. So I have this contraction of p hat t. And if I have some quantitative estimate of alpha, instead of just show that alpha is smaller than 1, then very good. You have the same term on right-hand side and the left-hand side. And then this gives you the control that this distance is a bit smaller than epsilon times 1 minus alpha inverse. So that's why it's really important to get a quantitative estimate of alpha instead of just saying that, I constructed one Lyapunov function and there is a minorization condition and such that this alpha is strictly smaller than 1, but sorry, I don't know how small. So you really need a quantitative estimate of alpha. So that's why we need a coupling. Well, so for the finite time analysis, that's I would say standard. You just here the distance we use is 1 by 16, and then we estimate this finite time error. So which means, well, you cannot make your time step to be arbitrarily small, but you can do the extrapolation. You run it for time h for one round, and then you run it for time 2h for another round. And then if you know the order of accuracy of your scheme, then very good. You know you can do some extrapolation, and this extrapolation tell you how different is this this finite time truncation error? How big is this finite time truncation error? So this is just some finite time analysis, and then the Monte Carlo. So you run the coupling method to get the speed of contraction. So basically, you just run a large Monte Carlo simulation. You get the probability distribution of coupling time, and then you fit it in the log linear plot. You get this exponent. Then there is an estimator. I mean, of course, there would be a prefactor ahead of this. There would be a prefactor that you don't know. So if you really want to make things better, and you really want to get some absolute upper bound of your sensitivity, then you can do some extreme value theory, which means you run lots of coupling trajectories, and you only run it up to t, and then you measure what's the percentage of them that are coupled, or randomly sample the x and y in your domain. And then you have lots of coupling probabilities. And then you can use something called extreme value theory to see statistically whether the prefactor of whether your coupling probability is bounded or not. So I mean, it's I mean, this is a statistical tool, but it's quite useful. But, yeah, so statistically you can decide whether the coupling time probability you get it is bounded or not. Then you can, if it's bounded, then very good. Have some alpha. Then this is really the so this really gives the upper bound of your sensitivity. Okay. So just let me wrap up the talk about two numerical examples. One is the ring example I showed you in the very beginning, just a 2D ring. And we found that actually we can find the estimator. So this estimator is obtained by just looking the exponential tail. And this one is that we really use the extreme value theory. You can see that this bound is more generous. And what is the empirical error? Because it's really simple. So you can run a larger scale Monte Carlo, and then you have some extrapolation of your sample size, and it's about 0.0015. Okay. So the conclusion is that first, these two estimators are quite accurate. You are not wasting too much about this, even if it is upper bound. And the second one is that the Monte Carlo sample, the Monte Carlo sampler is really trustable. So that's the coupling time distribution. You can see that you can have quite precise measurement of the slope. Okay, and that's the extrapolation I said that you just increase your sample size and then you use a linear extrapolation, then you can get some good estimation about how your numerical error different, how is your numerical invariant probability matter different from the real one. And let me show you a counter example that the numerical the Monte Carlo result is not really trustable. So the Lorenz 96. Okay. So when you run Lorenz 96, you realize that it's really chaotic, especially when the dimension is high. So in dimension 4, it's a very strangely shaped limit cycle, and in the dimension bigger than 5, it's chaotic. Okay. So we find that it's really chaotic, such that it's highly difficult to control the truncation error. So in a way that you choose a really small step size, and then you run it, and then you find that your final time truncation error in general is still quite large. And well, unfortunately, this is time that you need in order to let your operator, in order to let the operator contract the W1 distance enough, such that you have some meaningful estimation. So which means the time you need in order to make things converge, you already see some dramatic, really dramatic truncation error here. And it's even worse in dimension 5, that you can see that this is your truncation error. So and this is your at this time, yes, you can see there are some contraction. There are some contraction because it's because you have noise and you have this strong chaotic, strongly mixing. But at the same time, this high level of chaos really amplifying your truncation error by a lot. So the conclusion is that even if for your H at the magnitude of 10⁻⁴ or even 10⁻⁵, the invariant measure is not trustable. It's not trustable because the truncation error grows much faster than the speed of contraction that you can observe. Okay, so that's just one good example and one bad example. So basically tell you that you can use coupling to do some sensitivity analysis. And as I said, we only did one simplest case, that sensitivity against the truncation error, but it does not have to be like that. You can make it, you can talk about the sensitivity against other parameters. Okay, so I think that's all about my talk, and just a few references about my recent papers. Okay, so thank you very much.
Thank you, Yao. Any questions from the audience?
Hi, yeah. On the first part, when you were talking about the alternating
Yes.
optimization method, yeah. I think I had one student who I taught him to check like how we impose boundary conditions for a boundary value problem, and I thought compared to what we're doing the weights, and you can have dynamic weights, by the way. I told you that, and I think that this method didn't come out very well, very stable. I think we got worse results than what we're doing.
Okay.
We don't have any concrete. I mean, I don't know if some data remembers I asked Varun to do that, but I mean, we're still checking it just for boundary value problems to see, like, you know, so you impose the equation, then the loss in the equation, then on the boundary, then back in the equation, and so on. So for a stiff boundary value problem, and the self-adaptive weights seem to be working very well actually for that case.
I see. So we didn't use the self-adaptive way because, as I said in the talk, so things like in the beginning and the end of the training process, the magnitude of two loss functions reversed. In the beginning, L2 is much bigger, and in the end, L1 becomes much bigger. So it's difficult to find a weight. I mean, before we have tried a few different ways to set up a weight, and none of them give us the promising results.
Yeah, it may be problem dependent, but I also asked my colleague, who is expert on optimization, Jerome Darpon, and he said he doesn't know any proofs for that.
Okay.
Yeah.
Okay.
Hi, Dr. Li. This is Chen. I have a question regarding the stochastic heat equation example in the first part.
Yes.
Yeah, so actually I'm curious about when you are saying the ground truth, like, is it there, like, does it mean there is an explicit formula that you are comparing with?
Yeah, here we just feed the neural network with the analytical solution, because in this case we know the analytical solution. Here I'm just testing the representation limit of neural network.
Okay, so like, did you compare with the neural network with some other methods like Monte Carlo or some like traditional methods?
In dimension 10, I don't think the traditional method works unless you use something called the sparse tensor, which is really difficult to program if you know it. There's something we call the sparse tensor.
Okay.
I know that it works in dimension up to 12, based on what I have heard. But that's not something that is very easy to program.
Okay, yeah, that makes sense.
Any more comments or questions? Well, if not, let's thank our speaker again. Thank you, Yao.